Welcome to HYSKY Monthly, August 17th, 2026. And this is our 80th. Goodness. So we're 20 webinars away from our 100th episode. So welcome to the 80th episodes of HYSKY Monthly. HYSKY Monthly is hosted by HYSKY Society, and we're a 501c3 charitable educational nonprofit dedicated to the decarbonization of aviation and aerospace through the use of hydrogen. We do this through connection and community, advocacy, awareness, and education. So one of the big things that you've heard a lot of us talk about and really the foundation of HYSKY Society is the hydrogen aviation ecosystem. If you're building an aircraft that's electric or has a hydrogen combustion engine or just a non-traditional aircraft, you typically aren't working directly with the people producing your fuel source. And that just isn't feasible for hydrogen aviation to take off. So we really needed everybody to be talking. So often we would find, the fuel cell people and the onboard storage were talking to the aircraft, sort of like these three groups. And then we would find the hydrogen logistics, and the refueling were sort of in a group. And we needed to bring all of that around the aircraft and really the airport as well. I need to stick that in there. But that's what we mean by the hydrogen aviation ecosystem. So if you produce hydrogen, we need it. So you're part of the hydrogen aviation ecosystem. If you move hydrogen, you're part of it. So you don't have to specifically be building an aircraft to be part of this ecosystem. So just a quick, go through some quick announcements, and then we'll get into our speaker. We have Flying High coming up on November 4th. And actually this time we've updated it to 8 a.m. to 6 a.m. I mean, not 6 a.m. Goodness. That'd be a long conference. 8 a.m. to 6 p.m. Central Time, because we've got so many amazing speakers. So make sure to register for that. It's only $75 to attend. We have sponsorship opportunities available starting at $250. It is virtual. Last year we had over 300 people. We expect the same this year. So it's just a fantastic group of people. Everybody you would want to hear from, you're going to hear from at this event. So go ahead and scan that code and register. Flying High. This is our 4th annual Flying High, which is crazy. The first 2 years we did it in person. The first year we did it in Grand Forks, North Dakota. The second year we did it in Las Vegas. The third year we did it virtual. The fourth year we did it, we're doing it virtual. Next year we're planning to do it in person again, but get involved in this virtual one because it'll give you a lot of insight into how it will be in person. And if you've been to the previous in-person ones, then you kind of have an idea. So we're always looking for partners, sponsors, speakers, papers, all of that. So make sure to get involved. Okay, I'm going to pass it to Rishav now. Just a quick preface to what Rishav is going to say. So yes, we're a hydrogen aviation nonprofit, but you can't really have a conversation about hydrogen aviation without talking about sustainable aviation fuels and vice versa. And here at HYSKY, we tend to spend a lot of our time looking at hydrogen fuel cells, hydrogen-powered aircraft, batteries. We don't look that much at sustainable aviation fuels. And we know that sustainable aviation fuels can really help bring down the cost of hydrogen because they can use hydrogen as a feedstock. So we thought it was necessary and very relevant for us to offer a course on sustainable aviation fuels. And so Rishav is going to talk a little bit about that.
Thank you, Danielle, and welcome everyone once again to HYSKY Monthly. Danielle said it's the 80th episode, and it's been really good going for all of us. Thank you for being part of HYSKY and HYSKY Monthly for all this time. And like Danielle said, we need a transition fuel as we are decarbonizing, and what better way to do that than through sustainable aviation fuels. And this time we've again teamed up with AIAA to offer you this course, Advanced Sustainable Aviation Fuels and Aircraft Design. It starts this
Rishav,
22nd of September.
Sorry to interrupt. It was sharing, but then I don't see it. Am I missing something? Do you guys see it? I saw it for a second. Maybe stop and reshare And if it doesn't
Okay.
work, I can share for you.
Right, please do that. I'm sharing it right now. But maybe my
Yeah, I don't
bandwidth's
know why
kind of
we're having.
bad.
I don't know. It never works with me. um,
All
do
right,
you
I'm gonna
see
do it
it?
again. Sorry, everyone. I shared it. Do you see it?
I'm also sharing it.
Okay. All right. So let's. All right. So this time we again partner with AIAA, and we're offering you the Advanced Sustainable Aviation Fuels and Aircraft Design course. It starts 22nd of September this year, and it goes on till the 23rd of October, 5 weeks, 11 classes. We are very, very honored to be joined by experts in sustainable aviation fuel, Dr. Matthew Clark, Carlos Morao, Eva Malaviti, Joshua Haynes, Upendra Kandewal, and Shankarakas. This is going to be a really awesome course. We have 6 modules. I'm sorry about this. I'm scrolling a lot on this, but then we have 6 modules. So we have 6 modules on combustion, on combustion and engine integration, aircraft propulsion, design, materials compatibility, fuel systems, and safety. Then there is the aircraft infrastructure, logistics, cross-border SAF, SAF, supply chains, the MDO, digital frameworks, and lastly, there will be pathways, policy certification, and deployment. So courses AIAA is enrolling. Please go to the website, which will be put in the chat, and feel free to share this link with everyone. We hope you and your friends can join our SAF course. Thanks, Danielle.
Thank you so much, Rishabh. Sorry for the technical difficulties, everybody. Rishabh and I have had issues for whatever reason when sharing our screens with each other. Let me just put this link in the chat once more. And okay, great. So moving on. And again, that starts September 22nd. I'll just add it's Tuesdays and Thursdays, but the very last week it's Tuesdays and Thursdays and Friday. So there will be three courses, 3 lectures on that last week. I'm very excited about this course. I know very little about sustainable aviation fuels, and even looking at those modules when you were talking about them, Rishabh, I know I'm going to learn a ton. So, we try really hard not to make like HYSKY a hydrogen versus batteries or hydrogen versus SAF. And I think this is a really good way to learn and work together as an industry. And another thing I'll add, that these courses that we do, when we do them with AIAA or when we do them independently, they are fantastic networking. You're live, you're there with the instructor, and the people you meet are just so cool and impressive. I'm always blown away by the students that we have in the course. So it's just really good way to get connected, build relationships professionally, and all of that good stuff. So other ways you can get involved with HYSKY, which we've pretty much talked about 2 of them. HYSKY Monthly, obviously you know about that because you're here right now. And then Flying High, which is coming up in November. And then Rishabh talked about the courses, but then also I want to talk a little bit about HYSKY Connect. A lot of you are members of HYSKY Connect, and let me just put a link in the chat. This is our networking app that you can join totally for free. Yes, there are upgrades, and we're rolling out some very cool features in here, including news that you won't get anywhere else, including direct contact with people. And I'll just give you a little sneak peek of some of the members that are in here. And there are over 500 people in here. You can direct message them, you can email them. Some of them have their phone number. So I really encourage you to go to connect.hysky.org and create a free account if you've not done that already. Here are some of our previous courses, and you can also find the SAF course in there to link you there. So kind of what that looks like. Here's our certification course, and it's got all of the materials. So anyway, definitely go in there. This is where the meat of HYSKY lives. And we're rolling out new features in there every day. So create your free account in there. And we also have HYSKY Pod exclusive. I was able to interview him and we talk about what he's up to now. Just a very good conversation. And we dive kind of deep into something because one of the questions I ask him are like what the US could have done differently to maybe make Zero Avia stay more active in the United States. And he talks about some stuff that the UK has done. And I just thought it was really insightful. And then we also talk about AI and consciousness and other things. So it's just a really great podcast. We're also always looking for podcast guests. And I put the link to Val's interview in the chat. So make sure to subscribe to our YouTube channel. That's one of the easiest things that you can do to support us. And soon we are almost at 1,000 subscribers. So I'm very excited about that. Okay, so enough about me and HYSKY and all of that. I'm so excited to introduce today's speaker. Today's speaker is a dear friend of mine, Dr. Nick Ingarra, and he's going to talk about why a fuel cell plane makes sense. And so Dr. Ingarra is a also professional engineer, mechanical and chemical engineer with more than 20 years of experience advancing battery, fuel cell, and thermal energy systems across automotive, defense, and emerging technology sectors. His career focuses on electrochemical modeling, thermal behavior prediction, system integration, and performance validation, where accuracy and physics-based insight matter most. He spent much of his career working in thermodynamics, power and energy, and keeping complex systems at the right temperature. And I just want to add something before I pass it over to you, Nick. I have learned so much from Nick over the last, 6 months or so. And Nick has made some breakthroughs that I have never heard and I've never seen. And I think he holds the wisdom to what is really going to open people's eyes to the possibilities of hydrogen fuel cells and maybe expand their thinking beyond what batteries are capable of. So I'm going to tell you right now, Nick is one of the smartest people that I've ever met. You are going to want to watch this webinar multiple times because every time I see him present, I learn something new. So this is going to be a very technical and very educational webinar. But again, I just want you to take note that Nick has discovered some things that have never been discovered before, and he's going to be saying some things that have never been said before. So without further ado, Dr. Ingarra, the stage is all yours. Everybody, please give a virtual round of applause to Nick.
Hi, good morning, everyone, and good afternoon, depending on your time zone. So first question I would like to ask everyone too as well, this question has boggled my mind for about 13 years, and that is why does hydrogen have a color code but electricity doesn't? In every discussion in every industry I've been in, people have asked, it's got to be green hydrogen, blue hydrogen, gray hydrogen, but we've never done the same for electricity. So it's one of the questions I've always asked, like when comparing battery electric to fuel cell, why does hydrogen have the color code and electricity doesn't? The other item I'd like to also start with too as well to kind of frame everyone's reference. One of the many mysteries is how do we actually model a battery? On the left over here, let me turn on my laser pointer, kind of help see the screen. There's like a screenshot from a Simulink model which uses like a Kirchhoff's voltage law, which will compute the discharge voltage of a battery based on knowing what the state of charge is, what the resistance is, and what the current is. So we have a separate modeling routine for a battery, but a battery doesn't fall into any of the dependent voltage sources in the electrical engineering world. The only item that seems to fall into place is a fuel cell. It falls into place as a current controlled voltage source, but a battery doesn't fit any of these. And so Danielle already covered about me. So what I wanted to do to kind of gauge everyone, to get everyone's feet wet on the presentation, a lot of us have to work together to achieve the end goal. We need people to go, how does it work? How do I use it? How do I make it? How much does it cost? And how do I market it? And we need we need people in every one of the groups to convey this message. My area of expertise is how does it work? So I'm trying to help unlock everything in the how does it work end of it so we can move to so we can hand it off to how do I use it? How do we make it? How much does it cost and how do I market it? So a lot of this is going to focus on how does it work? And the other side note too as well is I kind of look at everything from a thermal background, from power in, power out, energy in, energy out, and inefficiencies lead to heat. So We're getting a partial thermodynamics lesson here too as well. And when we think about aviation or in general, we need to think of three different models that need to work together. We're going to have basically like the aerodynamics model of the plane, which is going to be used to determine the power and energy that's basically required. We're going to have a powertrain model, which is basically delivering power from the source to the propellers. In that case, so basically how we're delivering the power. And we also have the thermal model. And the thermal model's job is to take the inefficiencies of powertrain model and maintain all the fluids in the right temperature so we don't get power limiting based on, let's say, like a battery temperature, power limiting based on engine temperature. So we need all three of these models to work together to achieve the overall end goal. And just to kind of walk through the vehicle model and then the math. So we can take the aerodynamic parameters of the airplane, compute the power, and then with the mechanical efficiency and propeller efficiency, we can compute the amount of power the powertrain has to deliver. Note, when we're dealing with a vehicle model, we're dealing with the power at the end point. So we have to convert this power to what the powertrain needs to deliver, and that's normally done through the inefficiencies of the driveline. So you have to take the efficiencies of your, say, transmission in the other cases, the inefficiencies of like the inverter, all those inefficiencies to compute the actual power that's needed at the source. And another thing, couple points to keep in mind too as well. Batteries can only store energy, and like fuel cells in other cases, which is a key point, they can provide power on demand, like the internal combustion engine. And one other friendly note, when you're doing the vehicle modeling too as well, never forget to add in your accessory loads. So that's like your low voltage system, your climate control system. All those loads need to be provided that the powertrain needs to deliver. And now with part of the vehicle model, we need to understand power and energy. This reference came out of an ACS paper in regards to power and energy profiles. So when we're selecting a power source, we need to find something that can meet our instantaneous power demand and then basically our cruise demand and then our descent. So one thing to keep in mind too as well, as a point of reference, when we're dealing with internal combustion engine powertrains, they're providing power on demand. So like when we're taking off, we can hear the engines ramping up to a high power load to satisfy the takeoff, and then they slowly ramp down to provide the power for cruising. And in the cases, if you have a battery system, the battery would have to provide the power that's needed for takeoff and then provide cruise. And in the fuel cell case, we need to provide the on-demand power and the fuel cells on-demand power where we're providing the power for climb and the power for cruise. So we need to keep these in mind for the power and energy requirements throughout the whole profile. So we need to understand what our power profile is so we can compute the energy that's needed. And here's a case that's kind of borrowed from the automotive as a sample. So normally if you have, let's say your speed profile, you can compute with the vehicle model. You can compute your on-demand power that's needed, and you can do this for each case. So allows you to compute like the instantaneous power. We do this to kind of determine what the peak power is, average power, and min power is in the system. And then if we know power, we can jump back and we can integrate power to actually come up with the energy required. So in a study like this, you can determine how much energy or how much battery capacity that you need. And if you don't have enough battery on board, you can determine, hey, I need to recharge here and recharge here based on how many batteries I can package. So we have to use our vehicle models to basically get our power profile that's required. We need to integrate that to determine how much energy we need. And based on also knowing the power profile, you can also determine how big of the hydrogen system do I need to support my flight. And now let's take a look at the powertrain models too as well to kind of compare battery system to a fuel cell. So we have the propellers in both systems. We have the electric motors. We have the inverters in both of those cases. And then the other difference is where we're getting the electrons from. In the fuel cell case, we have the hydrogen tanks providing the fuel cell stack with hydrogen to produce electricity. Then we have a boost converter to step up the voltage and current, or the inverter to the motor. In the case of a battery electric, everything is solely coming from the battery. And one key note that we have to emphasize is that a fuel cell can provide power on demand, and the batteries can only store energy. So we're either withdrawing energy that we have stored, and then the battery can also accept energy too as well. So we have two different devices that do different things, but then they also complement one another. And to kind of touch on too is the really complicated system where I've spent most of my career is basically on the thermal system. So the thermal system is basically dealing with all the inefficiencies in the system where all that waste heat that has to be removed, and it has to handle like the heat exchangers to cool, let's say to cool the engines or to cool the batteries, cool the fuel cells. And in the case of batteries and fuel cells, we have to cool and we have to heat. And the thermal systems will also have to handle the HVAC for the conditioning of the air. In the cases of the fuel systems to cool the fuel, and also for the power electronics cooling. So the thermal system is one of the key systems that we need to look at when we're approaching aviation, because all three systems have to work together to actually get accurate results. And to add some humor and break the ice to make sure everyone's awake too as well, is that we need to think of batteries are like babies. They can't be too hot. They can't be too cold. They got to be kept at the right temperature. So we need to heat them and we need to cool them in those instances. And the fuel cells are like the diva, where we can't have them too hot, we can't have them too cold, but yet the only difference is we need to maintain the relative humidity and the water content correctly. Because if we don't maintain the water content in the fuel cell, we'll either lose efficiency due to ohmic losses or we'll lose performance due to flooding. Now, I'd like to compare both technologies to one another too as well. And I'm going to throw in some fun thermodynamics too as well. So in a battery case, so both systems are considered electrochemical systems that convert chemical energy to electricity. But here's some of the differences. A battery has 3 different discharge modes of constant power, constant current, and constant resistance. And I'll show those graphs a little later. The battery performance also depends on its C rate and its state of charge. And we'll have to also note that batteries can provide constant power, but not at constant voltage. And a fuel cell is different than a battery. It's a steady state device because it's like an engine, but it doesn't store the energy. It basically converts the hydrogen and oxygen into electricity, water, and heat. Fuel cells mainly have one discharge mode because it's an on-demand power source, and its properties are constant as long as you're providing the fuel. So when we get into the battery system, a battery is kind of like a closed system. So think of putting like a prime rib into an oven and the oven's sealed up. You have it sitting in there and you can only heat it or cool it by turning the knobs on the oven. So closed systems are a little bit harder to cool than open systems. Where open system is mass can enter and leave the system. So I can either cool a fuel cell by transferring some of the heat to hydrogen, transferring some of the heat to air, transferring the heat to the coolant. Batteries will have a limited energy capacity and how much energy they can store. Fuel cells will provide energy as long as there's fuel in the tanks and there's air provided. The performance of a battery will decrease as we're discharging more. We need to recharge the system. A fuel cell is a steady state device, and how we replenish it is with our tanks, providing it with hydrogen and air, and sometimes methanol if you have a methanol-based fuel cell. And one of the keys we need to also look at when comparing technology is one of the items I learned about was called the Ragone plot. The Ragone plot is basically comparing specific energy to specific power. So specific energy is how much energy is stored per kilogram. Specific power is how many watts I'm generating per kilogram. So this chart's comparing capacitors to ultracapacitors to flywheels to the internal combustion engine, the batteries, older battery technologies, and the fuel cells. Fuel cells have a pretty good specific power to the combustion engine. Batteries are somewhat close to the specific power. You have limited run capability based on the battery. So fuel cells can do the job, power on a little bit less weight, but we should also note that both batteries and fuel cells cannot replace the full power of the internal combustion engine. The internal combustion engine wins out on power and energy, but it seems like number 2 is the fuel cell and number 3 would be the battery. But keep in mind, it's not a one-size-fits-all scenario. Some cases you will need a fuel cell, some cases it will be a battery. We need both technologies to go forward in the aviation industry, and it's a case-by-case basis. And another type of Ragone plot is kind of comparing, it's the same item, but this one is kind of comparing different battery technologies to one another. The newer technology that's coming out is sodium. It's a little bit less on the power density, mainly because sodium is heavier than lithium, but it offers you some differences. Like you can fully discharge a sodium ion battery. Lithium ion batteries, you can't fully discharge to zero. You can discharge them. You have to keep their minimum cell voltage about 2.5 volts per cell. But you can see where the lithium ion energy and power density is. The only way to kind of maximize the energy density is with a lithium metal anode. And there's some companies that are looking into the lithium metal anode right now, but you need pure lithium metal anodes to push the volumetric density. And the other reason why the lithium ion batteries have a higher energy than sodium is you get 4.2 volts per cell. Sodium's approximate open circuit voltage is going to be 3 volts. And OCV just stands for open circuit voltage. And another plot to kind of show where the battery roadmap is going is you can see where we're at and where we're trying to get to. So there's solid state technology that's coming out. It's a few years away. Solid state batteries are going to have to be heated up to a particular temperature because you have no liquid electrolyte in there. So you need heat to heat the cells up to get them up to temperature so they can actually conduct the ions to maintain operation. So you can kind of see the past to where we're at and where we're going with the battery chemistries. And the other note with some of the battery chemistries right now, so lithium ion chemistries has several different chemistries. You have like lithium cobalt, you have lithium manganese, you have lithium iron phosphate, nickel manganese cobalt, NCA, which is nickel cobalt aluminum, and LTO, which is lithium titanate. So typically in batteries, you'll always have a trade-off chart because you can't have your cake and eat it too with the technology. If you get something that has good power density like LTO, but it's not going to have great energy density, so you're going to have like a weight penalty. So you have a couple different types of batteries. So you can basically break them down under power batteries and energy batteries. So power batteries are like your sprinters, and then your energy batteries are like your marathons. So those power batteries can give you rapid power, but they don't have great energy storage. The energy batteries can give you great storage, but they don't like to discharge extremely high power rates. So you can see there's always trade-offs on power, energy, cost, life, performance, and safety. So you have to find a battery that'll meet your requirements and also meet the weight requirements too, since weight is critical in aviation. And now here's some of the differences, kind of like doing an A to B comparison of the batteries to the fuel cells. So a battery is a storage device compared to a fuel cell, which is power generating. As we mentioned, we have a closed system, so no mass is allowed to enter or leave the battery. Fuel cells open. As long as we're providing mass to the fuel cell, it will provide us with our power. Our battery is a non-steady state device, so we have to model it differently compared to like a fuel cell, which is more of steady state. We can have constant power, but not at constant voltage. For fuel cells, we can get a constant power delivery out of it. For a battery, its efficiency is going to be continuously changing, and I'll show this a little bit later on with breaking down the battery data. Fuel cells have a steady state efficiency, so whenever you're hearing an efficiency calculated on a fuel cell, it's provided under steady conditions with a steady flow rate of fuel, steady flow rate of air, and a steady output. And another factor we need to keep in mind when selecting batteries and fuel cells for our application, chemistries have different operating ranges and can only do so much. Like for instance, the nickel cobalt aluminum chemistry can operate from 0 to 45 C. And keep in mind, these are noting during charge and discharge cases. So you can go up to 50 C for nickel manganese cobalt and 60 degrees C for LFP. So typically you can charge your battery between 0 and these temperatures, but when the temperature drops below 0 degrees C to minus 30, your battery can only discharge, it cannot charge. So if your battery is cold, you need to heat it up and precondition it for charging cases. So if you're flying up at elevation and your battery starts getting cold, you're going to have to warm it up to heat it to get it out of this temperature range so you can charge. Fuel cells, on the other hand, can operate from minus 45 to about 85 degrees C. And some fuel cells can have an intermittent temperature of 95, but it's always good to keep your fuel cell at 85 degrees C. Your charging is going to depend on your battery temperatures, what we said, the state of charge, and the current and capacity. Think of a battery like eating Thanksgiving dinner. Let's say you're starving, you start eating a couple rounds of turkey, you'll eat fast, and then you start slowing down as you start getting full. So batteries are like the same way. At low states of charge, they can take a lot of current. And as you start increasing the state of charge, then you have to start slowing down. In a fuel cell, it's mainly how much time it takes to refill your tank. And keep in mind, a plane on the ground is not making money. Other trade-offs we have to make too as well when it comes to cargo and range. Batteries don't get lighter as you fly, so your weight is going to remain constant during your flight. So you can't increase elevation as you start consuming fuel. You're going to reach a max altitude and be able to stay there. So you have to make trade-offs on cargo for battery weight. And on the other hand, fuel cells, we have to have a better power to weight ratio compared to batteries. So you can handle more cargo with the fuel cell over the batteries. So batteries are going to be limited by range, how much battery you can put on board. And for fuel cells, you're basically going to be limited by your hydrogen storage. So batteries could be good for short range applications. Fuel cell could be good for long range. And it also, if you factor in payload, your fuel cells can handle much higher payloads than the batteries. Now, here's a precursor on battery efficiency. So right now, when you say a battery efficiency is batteries between about like 90 to 95% efficiency, that's based on the combination of the coulombic, or sometimes on the Faradaic, and the voltage efficiency. So the coulombic efficiency is basically on discharge over charge ratio. So how much charge am I taking out versus how much I'm putting in? And the voltage efficiency is my average discharge voltage divided by my average charge voltage, which is based on energy out over energy in. But this efficiency doesn't tell me real time what's going on. This tells me like on an average from point A to point B, what this efficiency is. It does not tell me real time what it is. And if we propose a new efficiency based on the discharge voltage divided by the open circuit voltage, which is actually going to be a real-time efficiency because you can actually calculate this based on state of charge and current, you actually get different efficiencies of the cell basically based on different C rates and different state of charges. So you can see that the C rate impacts your efficiency, and also your state of charge basically impacts your currency. So now you have a dynamic map now for the battery. So its performance is changing real time on how efficient the battery is over like 100% to, let's say, 10% state of charge, because we could never hit zero. So this is a proposed efficiency change that we need to make for batteries, which is eventually going to impact how we model battery systems. And I'll jump into a point I've emphasized before. Batteries have three distinct modes of discharge: constant current, constant resistance, and constant power. Which one do we need for our application? Well, the answer is it's going to depend on the load depends on the type of load that you put on the battery. And we'll also have to note that the resistance, the voltage, the power delivery, and efficiency are all a function of the state of charge, the C rate, and temperature. So we have to start modeling batteries dynamically. And one other side note too as well is that if it's a hybrid system, so if the battery is paired with another component like an engine or fuel cell, you can control the state of charge of the battery and therefore then almost getting constant properties out of the battery. But this can only be done if you have another power source and the battery is not the only power source. So let's walk through the battery. So here's a sample discharge curve of a battery showing, based on different currents, how the discharge voltage changes with capacity. So you'll note that as the state of charge decreases, your discharge voltage is decreasing. And this is done at a constant current case. So under constant current, your voltage is decreasing, but your current is remaining constant. As a result of this, your power is not going to be constant. Your power is actually going to be decreasing. And these samples are your real-time voltages at different capacities. On the other hand, a PEM fuel cell, basically the fundamental unit of a PEM fuel cell is a polarization curve. So the polarization curve, based on providing a given amount of hydrogen, a given amount of air, you're going to get a discharge voltage based on a current density. And as the current density is dropping, you can see what's happening to the power. So voltage drops, current starts going up. So it's analogous like an engine curve where you have like a peak torque and a peak power. In this case, you're going to have like a particular voltage, and then you can see what happens to the power, and then you're going to have a peak power on the fuel cell. So I guess your ultimate goal for fuel cell design is to try to hit an optimum peak power point of what's going on. But these values are steady state values as long as the hydrogen and air are flowing to your fuel cell system. So let's get into the discharge modes of the battery. So as previously mentioned, we have constant current. So you can see right here, and bear with me being colorblind. So if I get the colors wrong, I apologize. So you can see a constant resistance charge, the voltage will run the longest time. And at a constant resistance, the current is going to adjust to basically maintain a constant resistance. This case is rarely used, but you have a constant current discharge, which runs for a period of time, but then your constant power case will run the shortest amount of time. And for constant power, your voltage starts dropping greatly because your current is going to be continuously increasing. So what happens in the constant power discharge, which will affect your modeling, is that your current starts increasing as voltage decreases. So what does this mean? So as current starts going up, your heat generation is going to go up between joule heating, and actually the electronics can actually get a less efficient, and you have to size your thermal system differently. So you're going to need more rugged cold plates to get the heat out, and you're going to need to kind of prep for more heat generation that you're coming, and you're going to need a pretty good thermal system. So you can see constant current discharge, current remains constant, but under constant power, your current is always increasing as a result of your voltage decreasing. And please keep in mind, a battery is not a steady state device. And so when you say C rate, you're not actually getting constant power. So I mentioned before that the discharge voltage of a battery will depend on its state of charge and current, and the battery's not a steady state device. But I'm going to break down battery data and show you like what the true resistance is of like this cell, the power delivery and the heat generation of this reference cell. So by breaking it down with a method that I've developed, you can actually see how the resistance of the cell there's a pretty stable range between about 80 to 20%. And then you can see how the resistance starts climbing at about 20% higher. Your resistance starts to climb. And the resistance is a function of your current discharge and also the state of charge. And this gets into like the loss mechanisms of a battery, which are the same loss mechanisms of a fuel cell. You have like an activation loss, an ohmic loss, and a concentration-based loss. This is like your concentration-based loss region. So you can see your resistances are climbing greatly below 20%, but you have a nice stable region at between 80 and 20%. So what does this change in resistance do? This will affect the power delivery too as well. So like with the constant current discharge, you saw that as the voltage starts to decrease while current remains constant, so the power delivery is also decreasing, but you have a stable like in resistance between that 80 to 20%. From this point, you can see, so based on the power delivery, you're going to be left with more heat generation. So as your efficiency, as the power delivery goes down, your heat generation is basically going to increase. And what does this basically do? So trying to refresh this in some old electrical engineering times before. So here's just a sample of a DC motor with a voltage source. We have an inductance, resistance, and then basically the DC motor. But we have to model these systems completely differently. In the case of a variable input voltage, so if this is replaced with a battery, my voltage source is not constant. My input voltage is actually decreasing. As a result of my input voltage decreasing, I have to adjust current in other cases to maintain a power. So you can see I have a separate differential equation for modeling with a battery. And then with a fuel cell, I have a constant voltage in this case, and I'll have two completely different systems. So we actually have to model both of these systems completely differently. And the efficiencies of the battery change are going to affect the variable voltage current model, or the variable voltage circuit model. Sorry, it's a little bit of a tongue twister. And we'll have to keep in mind with batteries that you have two different modes of charging that you'll refer to. You'll have a constant current mode of charging, and then you have a constant voltage charging. So what happens is during constant current charging, your voltage on your battery is going to be increasing. So the charger is going to increase the voltage on its end to maintain constant current up to a certain point. But with lithium-ion cells, we cannot risk overcharging the lithium-ion cells to get thermal runaway. So then we eventually have to transition to a constant voltage point. And when we have a constant voltage point, we set the voltage constant, and then the current is going to be changing. So we have to do this at approximately around 80%. That's why with our battery electric vehicles, you can rapid charge up to 80. And then it takes the longest, the remaining 20% takes the longest, because you have to go with a constant voltage charge at that point to get it to 100%. And then keep in mind is that a grounded aircraft, we're not making money. So we need to try to minimizing charge time. and we need to factor in charge time. And then here's an overlay of how you would do charging for a pack. So you can see under constant current, you charge up to a particular time. And during that time, then you switch over to constant voltage, and you can see how the charge current drops off to do the charging. So it takes a lot to get. So this is the easiest part. It's just the hardest part, getting that remaining 20%. And we'll have to keep in mind too, and if there is a cold battery, then you need to actually charge. You have to charge it after you warm up the cell. You need to get the battery above 0 degrees C to basically prevent like dendrites from forming and to get good charging. We've done the comparison of the powertrains. So I'm going to go into one of the topics of comparing technologies of battery to fuel cell is basically what's called pump to wheel. So it's basically borrowed from the internal combustion engine, basically from pumping in the fuel to the wheels. So initially, I was told that batteries are much more efficient than fuel cells based on like 70 to 75% versus 35 to 45%. But this is based off of a 95 to 98% efficiency. And if we actually look at the real-time efficiency of a battery, this will actually bring this number down, which will impact the inverter, the electric motor, and the drivetrain. So this efficiency was based off of the original non-real-time efficiency. So that's how the comparison of battery electrics to fuel cells efficiency war basically started. So the battery efficiency is going to be changing real time, and this needs to be taken into account with this comparison. And to elaborate on the point before, so pardon the pun on current research. So there's going to be an article that's going to be published in a magazine called In Compliance, which is going to go through this in detail. So one of the findings of some of the research that I did was that input voltage will affect the current draw on a system under a constant power discharge. So if you look at here, so I took a battery electric vehicle, I ran it from 630 voltage up 630 volts up to 800 volts and put a constant power load on it. As you can see, in certain cases, as the input voltage increases, the required current decreases. So how does this impact me? So what happens is at higher currents, we're going to have joule heating, which is going to lead to higher heat generation in that case. So the reason we went to higher voltage is to lower the current. But in a battery system, as voltage starts to come down, our current's going to go up, and so is our heat generation, which is going to impact the efficiency. And what I did, this is as a A to B to C comparison of the technologies to one another from a previous chart. And what I'm showing is so WOW is worst of the worst case, and Bob is best of the best. So if I assume the constant efficiencies of the batteries, what we talked about before, we'll state that a battery electric at worst case could be 65.4% compared to best case 84%. And if we change the efficiencies to show, based on that one cell, I showed like 98 to about 75% efficient, we can see that the efficiency drops to about 51.6. And we should also note why there's stars here is that as the input voltage changes, these components our efficiency is going to have to be calculated real time based on changing input voltage. And then based on the fuel cell, we can see that its worst efficiency is about 34.4 compared to about 51.4 for best case scenario with 60%. And then so a summary, what we're going to have to say is we're going to have more modeling complexity that we have to model battery systems dynamically is what we're going to have to do going forward on the battery side. And in the main reason why a battery is not a steady state device. And then the other efficiency for kind of calculating between what's called the Welt wheel efficiency, it's a way of comparing from the overall source of the power to the wheels. And as before, one of the reasons why the battery electric was dominant is because of this 90 to 95% efficiency, which is not a real-time efficiency. So you can see like your hydrogen from electrolysis is about 25 to 35% from electrolyzing the hydrogen to the wheel. And let's say if you get the hydrogen from natural gas, the overall efficiency is about 30 to 40%. But the pump to wheel efficiency doesn't change. So it's depending on how you get the hydrogen is where this comes from. But here's the key difference in battery electric. This is not a real-time efficiency. Now I'm going to get into the challenges for the fuel cell for going forward. So one of the key issues with the PEM fuel cell is basically what's called flooding. And what flooding is when you get a buildup of liquid water on the cathode, and this is specific to PEM fuel cells mainly. So as you get liquid water on the cathode, you have to get that water out. And then if you don't get that water out, you're going to lose your oxygen concentration, which is basically going to pull down your cell voltage. So if you don't have any flooding, you can get a higher current density, which is therefore higher power. So we have to be able to manage the water and the heat to basically mitigate the flooding on the fuel cells. And why does this occur? And that is because when we measure the water flow across the membrane of the fuel cell, we're measuring the summation of all the fluid drivers present. So we can't measure an individual fluid driver by itself. We can only measure the summation of all the fluid drivers. So a better way of looking at it, there's two numbers that add up to 3, and you can't guess what one of the numbers is. You can't say one number is 1 and the other number is 2 to get 3. You have to be able to determine them mathematically and from theoretical models to know how much of it is electroosmotic drag and how much of it is back diffusion. This is the electroosmotic drag and this is the back diffusion. And keep in mind in a fuel cell, or keep in mind that there's many different ways to drive fluid flow. We can derive it with temperature, with concentration, voltage, and pressure. So we need to have a good understanding of how pressure influences the water flow, how the voltage does, the concentration difference, and the temperature affect the water flow. And currently, the Nernst-Planck equation only takes care of these two, the concentration and the voltage. So we still have to assess the thermal effects. The other item that impacts the water management on the fuel cell, we have a lot of variation in these electroosmotic drag and back diffusion coefficients. So there's several empirical models out there, and each one, based on the hydration state of the membrane, is giving different values. So we have a lot of scatter in these coefficients, and each one of these can lead to different effects on calculated water flow across the membrane. The same can be done with back diffusion. So we need to find out where these models are valid, and we need to get these models kind of condensed down to which ones are applicable, and do they have other fluid drivers baked into them? Because what could happen is they might not have separated out the other fluid effects. And the water flow across the membrane is very complicated. It's nonlinear in some cases. In some cases, it's pretty linear. So, and this is a result of the membrane properties continuously changing. So we know, there's a speculation out there that the electroosmotic drag is not a function of current density. We have to understand the mechanism better. We have to understand how the membrane thickness impacts the total water flow. We have to analyze these systems to extract the proper transport coefficients so we can better understand the models that I showed on the previous slide. And here's like a sample case of one of the models that was done. So what they did was they forced the trend line through the 0, point, which assumes that no other fluid drivers are present. And by doing this, we don't know if the back diffusion was completely negligible or not. So we basically refit the data. So if you fit it to a linear trend line, not through the origin, you can actually see, okay, this term right here can go with this A1 term. This term right here can go to the A0 term. So if you just fit it to a line going through the origin, you're lumping this back diffusion effect into here, which is one of the reasons why there's speculation so much scatter in the electroosmotic drag and back diffusion models. So based on time, I might have to jump ahead and skip a few slides. There's about 12 more, and it's 12:30. So what'll happen is based on these coefficients, you can either see if their coefficients are the same sign, the other effect is working with you, and you're going to actually overstate your effect. And if the other side, if the coefficient is negative, it's actually working against the other driver, and it's going to understate how much water, and this will affect your balance of plant. It's going to affect the rest of your fuel cell sizing. Then here's how the method that I basically did my doctoral work on how to separate the water flow. So basically, if you take your partial derivatives of the equation, you can get the electroosmotic drag term, you can get the back diffusion term with some good old partial derivatives and equations of state. Then if you set the equations equal, then take the partial derivatives of your terms, you can actually compute the electroosmotic drag coefficient based on the experimental data and validate the model. So this is what I did my whole PhD work on, the electroosmotic drag and back diffusion. So let me know if you're interested talking about that in detail. Then if you have the nonlinear case, you repeat the same method and you can solve for the electroosmotic drag coefficient, which will allow you to help validate your model and help improve your water management. So when I refit the data that we saw before, I'm seeing the data doesn't go through the origin and I used a non-polynomial fit because I had some non-linearity in the data just to get a good accurate case. And then you can see at 95% relative humidity, which gets into a mechanism of single phase versus two phase, to try to capture that phenomenon. And when you process the data this way, you're actually seeing the electroosmotic drag coefficient as a function of current density. So we need to understand this mechanism even better, why it's changing with current density. And then when I process the data even further, I'm actually seeing these red bars should not be here because this is the back diffusion effect. So that one original model said the back diffusion was negligible. It's not, and it actually does contribute. So that's part of the reason why we see some of the scatter on these electroosmotic drag coefficients. Another item to keep in mind too with the temperature driven effect, we have many different researchers saying the direction of flow is either cold to hot or hot to cold. And there's no consistency with the magnitude nor direction. So we have to do additional research and understand how this temperature driven effect influences the water across the membrane, which will help out with the water management. The other item we need to look at in a fuel cell, so we need to understand this optional component that's basically added in. It's called the microporous layer, or the MPL. Some fuel cell stacks will have a microporous layer, which is a hydrophobic material used to try to eliminate liquid water. So with the one experiment here, a cathode microporous layer helps push you to higher current. And when you start transitioning down here, this means that you're actually flooding. So with no microporous layer, we start flooding at a low current density. When we add an anode and cathode microporous layer, we can get a little bit higher current density, but with the cathode microporous layer, we get the maximum current density. And you can see here, this is the direction of the water flow across the membrane. So the cathode microporous layer pushes the water negative, so it's going toward the hydrogen side. And you can see how the microporous layers also influence the electroosmotic drag coefficient. The other phenomenon that needs to be understood is called the Schrodinger paradox, not the Schrodinger cat experiment, the Schrodinger paradox. So what happens in the Schrodinger paradox is, which is kind of contradictory, is that when you put water vapor in a fuel cell, you get so much water vapor that moves across the membrane. But when I put liquid water in the fuel cell, I get more water transport across the membrane, which is a contradiction. We expect more vapor to move versus liquid. So this phenomenon was discovered in the 1900s, and no one has found a good solution to the Schrodinger paradox. So this is another item that needs to be addressed to address the water management in the PEM fuel cell. And also AEM is the anion exchange membrane, which is another type of fuel cell, which is different from an alkali fuel cell. And then the other item we need to address, how the water flow affects everything, is basically on the balance. So with a fuel cell balance a plant, you got a compressor, you got the humidifier. So the ultimate goal is we want to understand the water management so we can eliminate the need of this humidifier. I mean, we're still going to have a coolant pump. We're going to still have the heat exchangers, but we need to understand the water management so we can at least address the humidification and get good operation of the fuel cell. And then once you understand how the humidification works, you can understand what stoichiometry of hydrogen that we need to provide to the fuel cell, because that's how we humidify the hydrogen. One other page too we need to address is how do we cool the fuel cell? So one of the complex vehicles out there is the Toyota Mirai. It actually has two radiators used to cool the fuel cell. They're trying to maintain the fuel cell between 60 to 85 degrees C. It's called a main and auxiliary radiator. One radiator can't do it all. One of the reasons why, which I'll get to next, it's a tube fin technology and not plate fin. But we need to understand we need heat exchanger development to support the removal of all this heat from the fuel cell. So just to kind of quantify our heat generation and why we need heat exchanger research. So there's three cases right here with like 50 kilowatts, 150, and 300. And what it is, one of the terms that heat exchanger manufacturers use is what's called a Q per ITD. So it's how much heat I need to get rid of with respect to a temperature difference. So engines have a higher temperature difference at 105 C. I assumed 50 degrees C for the battery and like 85 degrees C for the fuel cell. And you'll notice here that the fuel cell heat Q per ITD is about 4 times larger than the than the internal combustion engine. So we need heat exchangers that can handle this high heat load, as you can see previously from the Toyota Mirai. And how we get there is several different ways. One of them was we have to increase the surface area of the heat exchanger. So this UA is the overall heat transfer coefficient. the fuel cell heat rejection only goes to the coolant. So we need something that can handle all this heat. So the rule of thumb for a fuel cell, so every kilowatt of electricity, I get a kilowatt of heat. So we need to increase the surface area as much as we can on these heat exchangers. And how do we do that? So in the case of the Toyota Mirai, they're using what's called like a plate fin heat exchanger. So you have, a tube fin heat exchanger, which has like these extruded tubes. So you don't have that much surface area going in. Plate fin heat exchangers is basically like making a sandwich, and you have hot side fins and cold side fins. So we need to increase the surface area with hot side fins, cold side fins. We need a coolant pump that can handle like the pressure drop and this heat exchange. And these are samples of different types of fins that you can use. So you need to optimize fins for their application. So typically for air heat exchangers, you need louvers. For coolant, you're going to need these Lance offset fins. And I'm sorry for running long. Then also we need to use the NTU method, which is the number of transfer units. This is a way how you can determine what kind of effectiveness that I can hit with a heat exchanger based on knowing how much the ratio of my hot thermal fluid and my cold thermal fluid. So in this case, a fuel cell, the hot thermal fluid is going to be your coolant. Your cold thermal fluid is air. So if you're trying to hit a particular, let's say like NTU target, you need to know, and you know your coolant flow, you need to solve for your airflow and the temperature difference. So sample NTU calculation and how to calculate the effectiveness. The other item we need to address is hydrogen storage. Here's a sample company that's not that far from me in Michigan called the Noble Gas Systems. They have like what I call this intestine style heat system for storing hydrogen. We need to find hydrogen systems that can fit in the form factor of a plane. These are formable, so something we need to look at into aviation. We need to commonize a way, whether between 350, 700 bar liquid hydrogen or cryocompressed. We need to also examine like how to get hydrogen into different areas too as well for remote locations, because hydrogen is portable. And in summary, sorry for running rather long, battery efficiency is not defined in real time, and we need to start looking at it in a real-time efficiency. This is what's making batteries appear more efficient than what they are, and we have to model the battery completely differently. We need to address the heat and water management of the fuel cell, and we need heat exchanger R&D to support higher heat generation at lower temperature differences. We need to look at total cost of ownership. And we also need to keep in mind it took 100 years to master the internal combustion engine. The fuel cell has only been around since 1969. And we need batteries for aviation, and we also need fuel cells for aviation. We need the batteries for like short range light load, fuel cells for long range heavy load. And we can't have a one size fits all solution. We need all technologies. We must capitalize on the strengths and the weaknesses of each technology so they can work together and help each other out. And lastly, we need to model the battery electric plane with a real-time dynamic efficiency. I think sum up my thoughts. And I guess the other main question is, since I've presented a lot of information for future reference, what topics would you like to learn about next? And I wanted to thank everyone for their time and listening to my talk. And I guess would you like to know more about batteries? Would you like to know more about fuel cells, powertrain, thermal discussion? I can talk about any of these topics in detail. So I'm going to say thank you for listening and any questions.
Nick, fantastic. Everybody, please give Dr. Nick Ingarra a virtual round of applause. And again, mind blown. I'm just so impressed with all of your work. And for those of you listening, I think that's my first time actually listening to the entire presentation without, I'm the kid at the front of the class with my hand up like, well, what about, and making sure I understand every equation. And normally when Nick goes through this with me, so I was chomping at the bits to ask questions, but I didn't want to interrupt you. But I've seen these charts and these equations. We've been going through them now for almost 6 months. I mean, the better part of a half a year. And for those of you that are seeing this for the first time, please do not feel overwhelmed, because this is Nick's entire pretty much dissertation. And I've seen this material quite a bit. I still have questions, but the big takeaway, I'll just summarize and Nick, correct me if I'm wrong, but really 2 things. Number 1, we need to be modeling batteries with real-time efficiencies because it's not constant. And then number 2, we need to be investing in more research for hydrogen fuel cells, the water transfer, and the heat exchangers. And I think there were a couple more, but those are my two big takeaways. Would that be correct?
Yes.
And so I'm going to ask questions from the chat. And by the way, if you have a question, feel free to raise your hand. I'm going to start selfishly with my question, which I've asked you before, but I want to ask it again. And you did cover it, but I'm asking it again for the audience. If batteries, I think like you had around 85%, if this is the case and we're not getting real-time efficiencies, why do people report batteries with 95 efficiency?
Well, that's because the way they model by thermodynamics, they looked at it from just those two Coulomb. They just kind of combine the Coulombic and the voltaic efficiency together. They didn't look at the overall use case. They mentioned, okay, I got from point A to point B. So tell me what changed from point A to point B, not what's going on while I'm going from point A to point B.
Mm-hmm.
So that's the difference, the real time versus non-real time.
Okay, so you tie it all together. And in Nick's last slide, he asked, what do you want to learn next? So Nick and I have been talking about developing a course on this. I think this presentation could be an entire course on its own. Did you see anything today, audience? This is for you, and then we'll get to the questions. Did you see anything today that you would want to dive deeper on? Are you interested in properly modeling batteries? Are you interested in further hydrogen fuel cell research? Are you interested just in general, everything that he covered today? Was there something specific that you would want to see turned into a course? So if there is something, please, let us know. And I'd love to hear from some of the experts in the audience as well. By the way, we've got some experts. I think you'll be excited when I tell you, Nick, who all's here at the webinar today. And so I'm going to scroll up and see the first question. And again, please raise your hand or come on if you have a question. Okay, Ross, I see your question. Feel free to unmute and turn your camera and mic on, and you could go ahead and ask your question. I don't know if Ross is still here. I'm just going to
Hi, sorry about the delay there.
Oh, there you are.
Yeah.
Hi, Ross.
Exciting presentation. Thanks. I also have a master's in mechanical engineering. I put in there as a note just as background for some of the context of the question. But I think I put in there basically was like thinking of recent developments in the gas turbine industry for aviation. They're trying to incorporate low emissions, hydrogen safe fuel injectors that they can just adapt into their fuel systems without having to redesign their entire engine. So with those kind of developments going on, do you see that competing? I guess it was like a broadly speaking kind of question of maybe if you have your finger on the pulse for these different industries for R&D, if you've heard of other developments that seem to be leapfrogging or out competing the gas turbine or combustion scene in terms of battery developments for competing on that graph that you showed with comparing all the different power plant technologies?
Oh, you mean the Ragone plot? So
Yeah.
I mean, hydrogen combustion is still not against. It's great. The only difference is with the hydrogen is that with a fuel cell, like with a PEM fuel cell, you cannot have carbon monoxide in the fuel cell. It ruins the catalyst. So what would have to happen for the hydrogen aviation case, you would need a different. You can have like lower quality hydrogen, so you might have some contaminants in the hydrogen, or for the combustion process. For like a fuel cell, I need like 99.99% hydrogen in that case. So you probably would need like two different standards of hydrogens. Almost think of it like regular versus like premium fuel in the senses for that case for the hydrogen combustion. So I mean, I'm fair game for hydrogen anywhere. Like the hydrogen storage systems would still benefit from H2 ICE I use ICE for internal combustion engine. Sorry, just have it from like, it still counts as turbine, but you do need, I mean, hydrogen ICE is a good way to go. Fuel cells is a good way to go in battery. So like the turbine engine probably might be able to take over in certain cases where the fuel cell reach its limit because the fuel cell still can't meet what the turbine engine can do. So I hope that answers your question.
Yeah, and just a quick food for thought was I've done research before in physics for metal organic frameworks as a storage method. When you pressurize it and then depressurize it, the hydrogen can be absorbed as like a crystal salt kind of form of solution. But I know there's challenges with that with the pressurization systems, and I'm interested to dive more into the humidification that you mentioned actually for the fuel cell plant design. I've been thinking about that personally for my own interest in HVAC engineering. Actually was like a total different industry, but there's a humidification problem there that's different. This is a different kind of humidification problem, but I'm interested in maybe diving into that myself too.
Yeah, we can talk offline for another case too as well if you'd like to, because I could go on for hours just on the water management. I wrote about a 600-page dissertation on that. So
Sounds good.
I couldn't sum that up in 5 minutes. I'm sorry.
Yeah, it's okay. Thanks.
Thank you for the question. I'll just add one of the, I guess, challenges in hydrogen aviation is that it's really difficult to find US-made hydrogen fuel cells. There just aren't really any manufacturers here. And what Dr. Ingarra has laid out is the proper way to model the areas of research. So, this is an opportunity. I made a comment in the chat for those of you that are part of the policy group. Nick's given us the roadmap for the areas of research that we need. I would love to hear from the two, researchers that are here. I would love to hear your thoughts, or if you have comments on any of the slides. Albert, I see your hand up. Welcome, Albert. It's been a while. I'm so happy to see you here.
Yes, hi. Nick, very nice presentation. 45 plus years ago, I worked on hydrogen for the car as well as the aircraft. And basically, the batteries progressed so much that hydrogen had no chance. And that's why we have battery cars. Now, you showed some new technologies in batteries, and some are much better than lithium-ion batteries according to the charts you showed us. My question to you is, what are the chances that this will happen again, that the technology of the battery moves so far forward to preclude the use of hydrogen that we see presently?
I think batteries are kind of reaching, like lithium ion technology, I think is kind of reaching an endpoint right now where they, for instance, like we've had certain companies try to go solid state, but like solid state batteries, you need to heat them up to a particular temperature because you start getting into issues of ionic conductivity in those cases. So you might be able to get like particular use cases where like solid state will work, but I think batteries are kind of reaching their limit of what they're trying to get to. That because at the end of the day, all a battery is two dissimilar metals that give you your voltage. So your lithium reaction gives you like 3 volts. I mean, you can only do so much with the cathode material. You can't pack more like lithium inside the cell, basically without a huge weight penalty. I think it's going to hit the limits, and we're getting to a point where this is kind of the limits of this technology, and plus with the physics limits of what's going on, you need to switch over to a different technology to go forward.
Well, really, my question is not on the lithium battery, but rather the other chemistries that you kind of flash through with.
Like the sodium cell is still like being developed right now as we speak. So it's going to have some pluses and minuses, but it's still going to have like a lot of limitations because like sodium is heavier than lithium. So you're going to have like some limitations with it. I still think hydrogen will excel. I mean, the sodium will kind of push based on its abundance. In the other case, it's much easier to get out of China. I'm sorry, excuse me. The sodium will be less reliant on China, but I still think it's not going to be as good as the lithium battery. It'll overcome, let's say, it'll overcome a little bit more of the better conditions in cold, but I still think it's going to be limited on what it can do, and you'll have like certain use cases for it. So, but at the end of the day, I think we're going to need batteries for a part, fuel cells for another part, and turbine engines for another part.
I agreed. And if in your comparisons, you add the turbine column on each one, that would be very nice. Sometimes you did, sometimes you didn't in this presentation.
I see him noting it.
I will make a turbine comparison.
And thank you for that feedback. We went through and we were trying to think of everything that we could compare to. So that's really good feedback. Thank you, Albert. Vadim, I would love to hear from you. I forgot to say, when you come on, make sure say your name, who you're with, and what your question is. My apologies, I didn't catch Ross and Albert. I know you're with
Blaze Tech Corp.
Thank you. Blaze Tech Corp. Yes, consulting firm. I knew that. Thank you. Okay, Vadim.
Right, Vadim Lvovich, NASA Glen, Cleveland, Ohio. Very nice presentation. Very detailed, and a lot of really good emphasis on important points. I mean, I also agree when you when you are mentioning that it's really not fuel cell against battery. It's, it's fuel cell and battery and hydrogen burning engine, depending on the mission, depending on the size of the aircraft, depending on conditions. They all have their uses and their places in the system. Certainly, what my comments are, like twofold. One of them, of course, when you're mentioning need for thermal system, of course, that's a tantamount importance. We are developing essentially electrical system, and it's a contained electrical system. Unlike, let's say, unlike internal combustion engine. Internal combustion engine has an exhaust. And that really alleviates a lot of thermal issues. A jet engine has an exhaust, also alleviates a lot of thermal issues. But when you're developing that electrical system, which is where heat is self-contained, you're kind of forced to either move to a different type of fuel cell. We had discussions obviously on like high temperature fuel cells, but where heat is of a higher grade, it's easy to deal with that. Or though you have to really like work more on radiators and just pay attention to overall system. Solid oxide fuel cells, they are even higher grade of heat, obviously, but they typically are not very very robust for transportation applications. I would like actually to hear your opinion on that. Is there a future for solid oxide fuel cells? And I see that that there are some questions on that subject as well. That's one comment. And the second comment, obviously, I really liked how you showed essentially that power versus energy balance for the batteries, but that balance, it also and overall that efficiency of fuel cells it's not a single efficiency of batteries. I'm sorry, is not a single number. It's a changeable number. But if you look, for instance, at fuel cells, and that also kind of comes to the manufacturing question. There is a peak for power and there is a peak for efficiency. And in general, it's probably better to orientate yourself towards maximum efficiency, but in that case, power is not as high, so you have to build more cells and just oversize your fuel cell. So I would like actually to hear maybe some of your comments about that. It also affects manufacturing capabilities. There was a question already about manufacturability, and you can oversize fuel cell, but there are also limits. There are objective limits to that. To how big you actually can make it, how big you can make MAA, how big is the surface area of MAA, also how many cells you can put in from manufacturability inside of the stock. So I guess that's a couple of questions which I just wanted to hear your comments about thermal management, use of different types of fuel cells in thermal management, and also for fuel cells, power versus efficiency. That trade-off. Thank you.
You're welcome. Well, the one thing I wanted to note is like solid oxide fuel cells. I'm not criticizing solid oxide fuel cells too much. I know they're very high temperature fuel cells between like 600 and like 600 to about 1200 degrees C is typically where they operate. So the drawback with that is once you get them up to temperature, you want to keep them running at that temperature, and they're good up to like the megawatt power range in those cases. So if you're in something that needs megawatts of power, or like high power, and you're going to be operating like at a long period of time for hours where you get it up to temperature, I would definitely go with a solid oxide fuel cell. It's just that getting it up to temperature is the hard part, and that's just my thought on the solid oxide fuel cell from that point of view. And what were your other point? And to your point, I think with the Ragone plots too as well. So it's kind of a quick aid of it.
If I could jump in, we are at the top of the hour. I want to be respectful to you, Dr. Ingarra. If you want to stay on and answer a couple questions, I will keep it going. But if you need to hop off, you can. It's up to you. But okay. You're not obligated to.
I have about 5 more minutes too as well, and then I'll put my contact information in the chat so people want to get a hold of me for other questions or follow up.
Awesome.
And then Vadim, I'm sorry, I was taking notes with the questions. You mentioned the solid oxide. What were the other 2 points that you emphasized? We
may have lost him while we're waiting. If he Vadim, you can come back on if you would like. Rajesh? Okay, there you are.
Yeah, here. They just lost connection for a second. What was the question?
No, I put on the thoughts about the solid oxide in regards to.
I feel that, yeah.
And then what were your other 2 questions associated with that?
No, my other question was about efficiency versus power, because peak of power is different from peak of efficiency. And our operating, it kind of like makes us generally make a selection between one or the other. And, and if it's, if we select efficiency, it means that we probably need to oversize the stack. And if we need to oversize the stack, then, then it also pushes us against manufacturability limits.
Well, the key thing, but in order for efficiency of the stack needs to be addressed, we need to basically fix the heat and water management of the PEM fuel cell so we can push it to higher current densities. That way you can get more efficiency out of a fuel cell. Because right now you're hitting a current density limit based on water management. And if we can overcome that with better understanding, then we can help improve those efficiencies. So I would actually do phase 1 first and improve the water management, then start tackling the efficiency. Because then if I can push a fuel cell to like 2 amps per square centimeter or 2.5 and understand the water, that's going to help improve the power density right then and there and help improve efficiency also. And I think I have time for like one more question that going to have to get back or I'm a dead man in the office.
Okay, perfect. Rajesh, if you're still here, Rajesh also had a comment with respect to solid oxide fuel cells. Rajesh, if you're still here, I would love to invite you to come on.
Hello.
Welcome.
Yes, I think I'm very clear in asking question. Is solid oxide fuel cell or solar cell technology is developed so that we can understand more about it?
Solid oxide
same
fuel
unit can be used as cooking generation and even for electricity generation.
So with the solid oxide fuel cell, it's a pretty good fuel cell too as well. There's always needs to be research in the materials on there because you're using ceramics and you're up to high temperatures in those. So you need some material development in solid oxide. Solid oxides, I would almost equate to like the turbine engine. Like if you're in those high like megawatts of power range in those cases, you can go with like a solid oxide fuel cell in those cases, but it's a pretty robust stack and like system. You just need materials that can handle those high temperatures is what you need. And just more R&D to improve that. But keep in mind, I've done most of my work on the I've done more of my work on the PEM, very little on solid oxide. So my apologies.
No problem. I wanted to just check whether the development is ready for commercialization. That's all.
Yeah, there's a couple companies in the U.S. I think like FCEL and like Bloom Energy. There are a few others, and they're kind of going in the data center route is where they're going based on the power demands that they need.
Shout out Bloom Energy. We were with them in Oshkosh. Thank you so much. Again, everybody, please give a virtual round of applause to Dr. Nicholas Ingarra. You can connect with him directly on connect.hysky.org. We will also share the slides and the video on YouTube. And Nick, just thank you so much again for this fantastic presentation. I'll share with you some of the info in the chat around future lectures that we might be able to put together. Thanks everybody so much for joining us for this 80th episode of HYSKY Monthly. Have a wonderful rest of your week, and we'll see you again in a month.
Thank you.